All right, so yeah, today we're going to launch into a little calculus. I'm super excited to do this. So, how does Einstein enter into all of this? Well, I mean, indirectly. So, this kind of just from, can't remember what textbook this is from. Might be our current one, I can't remember. The vision of human exploration by NASA to distant parts of the universe illustrates the idea of space travel at high speeds, but is there a limit to how fast a spacecraft can go? The word limit here is really important because it's not just a precise and descriptive word. There's a whole mathematical process that's going to come into play here that we're going to start talking about today. Okay. So here's the equation. In special relativity, Einstein first showed that objects that travel at velocities relative to another object, that they do strange things. Three weird things happen. Lorentz contraction says that any object that is moving at high speeds will contract along the direction of travel. So if I were to drive a really souped up sports car right down the middle of the classroom going some appreciable percentage of the speed of light, you would see that sports car shrink up substantially. And it really would. It really would compress. And I would see all you guys, the whole classroom, as being compressed because from my perspective, you're moving by me. Time dilation. Moving clocks run slow. So objects that are traveling very fast, as I'm traveling by, if I hold the big clock out the window of my car, you would notice that it was moving very slowly. The seconds would take much longer than 1 second. I would see the same thing if you were holding up clocks. Okay. And the third thing that happens is mass increase. Objects that travel at high speeds, they accumulate relativistic mass. They actually get more massive as they go faster and faster. And this is the equation that describes that. The relativistic mass of an object is equal to its rest mass. So the mass you would find if you massed it in Mr. Cooper's laboratory, divided by the gamma factor, which is the square root of 1 minus v squared over c squared, where c is the speed of light and v is your velocity relative to the reference frame that's measuring this stuff. Okay, so say if I'm driving by relative to the room, if I'm traveling really fast, we would be looking at how would the mass of the car change. Okay, and this is the equation that predicts that. Okay, so if c is the speed of light, the question is, what is the ultimate speed limit for any object that has mass? Anybody know the answer? Okay, I'm gonna leave you hanging. We'll get there. We'll get there soon. We'll come back to this exact problem in a while, and we'll be able to come to the answer using calculus. It won't be that long, pretty quickly. Okay, so let's start talking about the concept of a limit. And again, this is just so you, I mean, this is something that's kind of the start of our talk about calculus, but this is really a pre-calculus topic. We're not really doing calculus yet. This is something like in an AP calculus school. This is stuff that would have been done last year. Okay. So concept of a limit. Well, let's just explore a function for a second. If we have f of x equals this rational function x cubed minus 1 over x minus 1, what is f of 3? How would I find it? Yeah, I just evaluate the thing at 3, right? I'm going to get 27 minus 1 is 26 over 2, so 13. That's my answer, right? And if we pop into Desmos, we can see that. All we'd have to do here is just define that function. And we could evaluate this. And if we want to see that point on the graph, just do 3 And there it is, right there. Okay. All right, so what about, we got this thing all set up. Okay, what about f of 1? What's that going to give us? If I try to evaluate this thing at 1, what happens? Yeah, I get something strange. I get the top, I'm going to get 0. On the bottom, I get 0. Okay, what's 0 divided by 5? No, 0 divided by 5 is okay. It's 0, yeah. Okay, 0 divided by 0, though, is a problem. It's not in the same way, though, that 5 divided by 0 is a problem. 5 divided by 0 is truly undefined. This is not necessarily, well, this is undefined. The value of the function at 1 is undefined. But the behavior of the function may still be interesting to us. Okay, what we're going to find is the limit. We haven't even heard that word hardly yet, but pretty soon we're going to start talking about the limit of this function as x approaches 1, and that is not undefined. Okay, let's go back to our previous example here in Desmos, and let's just explore this a little bit further. First of all, let's do this. I want to be really tricky. I'm going to define A as being 3, and then I'm going to calculate, and I'm going to go up here and I'm going to make this a slider, and let's let this go from -2 to +4 in steps of 0.1. How about? Okay. So if I make this f of A now, I'm going to let A equal 3. It tells me 13. That's no big deal. And I'm going to make this point down here so we can slide it. I'm going to call it A f of A. This is a good introduction to programming, right? Because now what have I done here? So if I change the value of A, look what it's going to do. It's going to change the value that we're inputting into the function, and therefore it's going to change the x and y coordinates of that ordered pair, right? Okay, when A is equal to 3, you guys already told me, well, the output should be 13, right? And there's that point. Where to go? Why is that not showing up? Oh, I don't know why. Let's put in 3. There it is. Okay, I don't know why I did that. 313. Okay, what's going to happen, though, if I put in 1? Undefined. Okay, and I don't see a point on there because there is no point. The function's not defined there. However, if I drag this point, say I drag this point around a little bit, as I drag it down towards 1, it looks like it's approaching a value that we could describe, doesn't it? It's just that when we get there, it doesn't have a place to go. And beyond that, it's fine. There is literally what we call a hole in the function at that place. There's one little pixel that's missing, okay? All right, so how else could we describe this? Well, we could make a table out of this and explore the value this way. We could do something like if I go up to this first cell, and you guys remember doing this from a couple years ago? Vaguely, I'm sure we did it, but you may not remember it completely. Can anybody tell me how I make a table of values that correspond to that function? Anybody remember? Okay, you go up to the little gear and we click that icon, create table. And now I've got a bunch of values. Okay, let's start with something like, let's start at 0, how about? And then if if I establish a pattern and I just click along, you can see it gives me input and output values in my table. Look, it plots all those points too. Okay, there's all my points. There's one missing though at x equals 1 where it's undefined. What y value do you think that's close to based on those values? What is it? Looks like maybe 3, doesn't it? And we could do something like if we want to get closer, I could pick some values. Let's just delete a bunch of these and let's just start closer to 1. Like let's start at something like 0.99 and then we'll go 0.991. Oh, how come it's not? Does it not do that? Oh, maybe it doesn't. I thought it would. Maybe it doesn't do that. In Desmos, usually if you establish a pattern, it'll continue that pattern. Oops. I didn't do it when I didn't have the 0 either. Well, oh yeah, that's it. You're right. Yep, that's it. That's exactly it. That's it. There we go. Yeah. And we can see now as we get even closer to 1, at 1 it doesn't work. There's a hole in the function. But we can see the y value that it's approaching, that it seems to be getting close to. Now we can be a little more certain. It certainly looks like 3, doesn't it? We can't be 100% sure, but that seems pretty reasonable based on our table. Okay. All right, there's our first glimpse into the concept of a limit. Even though we haven't said anything specific, the way you're thinking about this is the way you're going to continue to think about this when we start introducing the concept of a limit. Take a picture of this guy and add this to our notes. Okay. So what is a limit? We just did a limit, but what did we do? So if we're going to define this function that we just looked at, and we want to evaluate the limit of that function as x approaches 1, and that's how we would say that. This is limit notation. This says the limit of f of x as x approaches 1. What does that mean? Okay, it means this. It means the value that the function is getting close to as x approaches a specific value. Okay? So in this case, we said that the answer was 3 based on the graph that we saw and the table. Okay? How come? Because the closer x gets to 1, the closer f of x gets to 3. That's the meaning of a limit. That's it. That's really what it is. Now, there's a little more. It seems pretty simple, but there's a few things we need to consider that make it just a little more sophisticated than you might have thought. Questions so far? Okay. Here is a good way to describe the flavor of limits. Imagine microscopic two-dimensional ants that live on functions on my Promethean board. These are our calculus ants. We'll come back to the calculus ants again and again. These ants are blind, but they have developed the ability to sense their position in the XY plane with perfect accuracy. So they're walking around on functions. They automatically always know what their coordinates are every little tiny ant step they take. Okay? The limit of a function as x approaches the value c really just corresponds to the y value on which the ants anticipate stepping when they get to x equals c. Okay? Now it turns out that sometimes the function doesn't necessarily even exist there like this one, right? This function, x cubed minus 1 over x minus 1, is undefined at 1. So the ants can't step there. There's no place for them to stand. The function doesn't exist. But the limit still exists because the limit is simply where the ants anticipate stepping when they get there. They never actually get there in the limit. So one really important thing to remember about limits is x is approaching a value but never actually getting there. In the concept of a limit, you never get there. You're just approaching it. That's it. So here's a good example of what a limit means in more of a physical situation. So let's say, I think I've done this before. We did this a couple years ago probably. Remember this example. I'm going to start here, and every second for the rest of eternity, I'm going to cut my distance to the door in half, right? 1, 2, 3, 4, 5, and so on. Do I ever get to the door? Never get to the door, assuming we can infinitely subdivide space, right? I never get to the door. There's no amount of time I could ever elapse that would cause me to get to the door. Are there any points on the floor between me and the door that I won't eventually step on or over? If I have an infinitely fine Sharpie and I put a mark on the floor that's not on the door, will I eventually get to that mark? Have to, right? Because I'm always progressing towards the door. So any point between me and the door I will eventually encounter, right? But I never actually get to the door. Okay, you might think, well, what about the point right next to the door? How could I get to that one? Is there a point right next to the door? Is there a point you can say that's exactly next to the door? How big's a point? How big is a point in math? Be brave. I'm hearing it, I think. Infinitely small. Yeah. It's infinitely small. So how many points are there between me and the door? How many now? How many now? Every step I take, there's always still going to be an infinite number of points between me and the door, right? So there is no such thing as a point next to the door. It doesn't exist in math, right? Because if I think I'm there, I just zoom in more and there's an infinite more points, right? So any point I make on the floor, that I mark on the floor, I will eventually get to, but I never get to the door. What's the limit of my motion? 1, 2, 3, 4. What's the limit of my motion? What's the door is the limit of my motion, right? How come? Because as time progresses and I take steps, that's the point that I continue to get closer and closer to, but I never get there. You get the idea? Limit is the place I'm trying to get, but I never get to. That's the idea of a limit in calculus. You never actually get there, right? You approach it with you can get arbitrarily close to that point, meaning as close as you want to get, but you can never actually get there, okay? So again, it's easy to convolute those two things. It's not what we did initially. It's not the value of the function. It's the value that the function is getting close to as x approaches a value. Where does the ant think he's going to step? Whether or not he's actually even able to step there, doesn't matter. Okay, give me 1 to 5 on that. How we doing? Okay, yeah, we need a little more, don't we? Okay. All right, so here's how we write that. Limit of f of x as x approaches c is equal to some number L. That's the y value that the ant thinks he's going to step on. That's the y value that we're approaching as the value x, as x gets closer and closer to the number c, whatever that is. Okay? All right. So let's look at some specific graphs here. Let's take f of x equals x squared minus 4 over x minus 2. Okay? We'll look at each one of those things. Okay, there are what the graphs look like of each of those three functions. Okay? In each of the three functions is undefined at x equals 2, right? Look at those graphs. In the first example, there is a hole in the function at x equals 2. There's one point that doesn't exist on that function, right? Second one, there's a break in the function, but neither one of those endpoints is defined. So again, there's a place where the function doesn't exist. There's no place for the ant to stand. And again, on this third one, it's undefined for a different reason. This time it's because there's a vertical asymptote there. So it's like a mountain that you can never get to the top of, right? In all three cases, though, the function does not exist at x equals 2. Okay? But again, if we just talk about that, that's giving us a pretty incomplete picture, right? Those graphs all look very different. In each case, the function's undefined at 2, but they still look very, very different. That doesn't tell us anything about the flavor of each of those three graphs. If we want to know more about it, what's happening at 2, that's where limits come into play. To express the behavior of each graph in the vicinity of 2, which is often really important to do, we need to introduce this concept of a limit. Okay, so let's inch forward a little bit. Let's look at this first one. Let's focus our attention on the portion of the graph on and around x equals 0 and x equals 2. Okay, now, what is the limit of f of x? And here's f of x squared minus 4 over x minus 2. We can just use its graph. We're initially going to evaluate limits or take limits. Those mean the same. That's kind of the language of calculus. This precise language is evaluate the limit. We're going to know what is the number value of the limit. Plug in something and get a number out. Plug in a number, get a number out. A lot of times we just abbreviate that in calculus and say we're just going to take a limit. It means the same thing. It means we're evaluating the limit. Okay, so we're going to start off using graphs and tables just to build up a conceptual understanding of what a limit means. And then very soon, we'll start to look at algebraically how can we come to these answers without having to rely on graphs or tables, which are useful but ultimately insufficient for us, right? This one works out great because what do you think? I mean, well, let's answer the questions here and you tell me what you think the answers are. What's the limit of f of x as x approaches 0? What do you think? What's the limit of that function as x approaches 0? There's an answer. We can see it on the graph. What is it? As x approaches 0. They're just, it's 2. Yeah, the answer is 2. How come? Why is it 2? I just made it. Okay, that means, okay, good. I get what, I understand where that's coming from. You're wondering, why do we have a 0 there? Because we just chose 0. Could be anything. Yeah, it could be anything. So we want the limit of the function as x is approaching 0. So we've got this function as x gets close to 0. I just randomly picked that. It could have been -1, +10, who knows? 0 was just a convenient one for our graph, okay? The answer is 2. How come? Is it because the value of the function is 2 on the graph there? I mean, if you said yes, I would say, well, yeah, that's kind of right, but it's not completely the story. Don't confuse, okay, now don't confuse this 2 with this 2. They're totally separate. Okay, yeah. So let me do this. In fact, just to prevent that, let's do this. Let me get rid of that one for now. Okay. There is. Yeah, there's going to be a limit for any value we plug in on this. But why is the answer 2? This is what I want. I want you guys to. I mean, indirectly, that is true, but that's not why. That's not why. No, you're right. I mean, You'll see here in a second, but that's really not the reason why. And I'll prove it to you. I'll prove it to you because now let's take. You'll see why. Let's take the second example. What's the limit of f of x as x approaches 2? What is it again? It's 4. You're right. It's 4. Okay. Okay. How come? Okay, because because remember what a limit means. A limit means in the terms of our, from our ant's perspective, as the ant walks, the blind ant walks along the function, as he's just about to step on x equal 2, what is his little ant brain telling him where he's going to be? It tells him he's going to be there, doesn't it? Now, when he steps there, I don't know, he just goes into a black hole or something. I don't know what happens, but he's got no place to stand. He can't stand on the function there. So when he actually gets there, he's going to be disappointed because that's not where he ends up. But that's not what the limit is asking. The limit is asking, where does he think he's going to be when he lands that last step? Okay? Not where he actually is, right? And he thinks he's going to be at that point right there, which has coordinates 2, 4. Okay, what's the question? It is okay, but it's exactly. It's like walking to the door. He's never going to get to that point, but where does he think he's going to be? Yep. Yeah. It could. In fact, that point could be maybe this is a function that's a piecewise function that has a point right there instead, right? You're right. Doesn't matter though. So okay, because in this case, like let me draw this a little better. Let me draw this point right here. Okay, so if that's the function, if it's got two pieces, it's got the line whenever x is not equal to 2, but it's got that one value when x does equal 2. So that function exactly. So here, let me write this piecewise function. The piecewise function equals x squared minus 4 over x minus 2 when x does not equal 2, and it equals a y value of 1 when x equals 2. Okay? So what is, for this function that I've drawn here, what is f of 2? Okay, what's f of 2 on this new graph where I added this point? It's 1. Absolutely it's 1. Because the point that the ant actually stands on has coordinates 2, 1. Okay, see my point? What's the limit, though? The limit is 4. Now we got to listen real carefully. See, this is why when Ashton said, because why is the limit equal to 4? And she said, well, because that's the location of that point. I said, well, okay, I mean, kind of, right? Kind of, but not really, because the limit concerns itself with where does the ant think he's going to end up with? What is the trend of the function? The trend of the function is as x gets closer and closer to 2, from the left or the right, the function trends towards the y value 4. That's not actually what you get when you step there, but that's irrelevant. The limit doesn't care with what happens actually at that point. All it cares about is what is the trend as you approach that point. Okay? That's how we got the 4, exactly, because that's where the ant anticipates landing when he takes that step. Yep, that's the behavior of the function, or the trend of the function, right? Is as x approaches 2, the y value is trending towards 4. Now, it turns out there's a surprise ending there, and you actually end up down there, but the limit doesn't care about that, because in the limit, you never actually get to end up on that spot. It's just where do you think you're going to be, okay? So then what about this first one? This is the one I meant to say. So when Ashton said, okay, the reason that the answer is 2 is because of this point right here that has coordinates 0, 2, you see why I would give kind of like that's partially correct. It's not because that's the actual value of the function. It's because that's where the function is trending. In this first example, it turns out that if the ant actually did step on 0, he would end up landing where he anticipated. But it doesn't really matter. Again, the limit doesn't really care where you actually end up. It's just where do you think you're going to end up if you're that little ant. In the second one, though, the ant thinks he's going to end up at a different place than where he actually ends up. The limit is equal to where he thinks he's going to land, not where he actually lands. Okay, is that clearing things up a little bit? Okay. Well, so a limit can be undefined. There can be no limits in some cases. There may not be a place that the ant anticipates standing. We'll talk about that. We'll get to that later. There's some reasons, some conditions where you can't actually define a limit. Okay, but on this one you can. Okay, and I think to clarify, I think what you're meaning to say there is a limit can exist where a function is undefined, right? Yeah. That's correct. But it can also exist where a function is. It is, yep. Okay. A limit can exist where a function is defined or undefined. And in this case, they're equally easy to find because you can see in both cases where the ant thinks he's going to step. Okay? All right. Question? Yes, limit is the prediction. Whether that actually happens, irrelevant. Doesn't matter. So the actual only limit is that 4, not like this? Yes. Limit 2 isn't a real limit? No, it is. It is because as the ant walks along the function towards x equals 0, where does he think he's going to land? At y equals 2, right? So what? Doesn't matter. The limit, you're going too far there because in the limit, we never actually get to go there, right? So the ant doesn't know if there's going to be a solid ground when he gets there or not. The limit is the same either way. Okay? Never actually get there. Right. Okay. And in this case, what's the limit of my motion? It's the table. I actually got there, but it was also the limit. Even if I didn't ever actually touch the table, you could still see that I'm approaching the table. So that's the limit. The fact that I get there is irrelevant. Doesn't matter. Okay. Isn't this cool stuff? I mean, like this is just so much better than any math you've ever done. And it is great. It is. It's just so much better. So what are the ways we can do limits? Well, for now, we're going to be really constrained. We're not going to do this analytically, right? We're only going to be looking at graphs. So you guys tell me real quick. I've got some function here that happens to be undefined at 1, but still the limit of f of x as x approaches 1, I can see from the graph is what? 3, exactly. Okay, so we got that one by evaluating or by scrutinizing the graph, right? Okay, it's all on the graph. We could also do this using a table. And I showed you an example using a table. Do I have a little? Yeah, I do. Okay. So if I make a table of values, right? So what are we doing here? We've got this function, f of h equals 1 plus 6h to the power of 1 over h. If I make a table of values and I approach 0, I can start to see a trend there. Now, it wants to know what did I just do? I never know. I never know what I'm doing. This board just confounds me on a daily basis. Okay, so now look at this one again, right? As h approaches 0, it wants us to type an integer or decimal rounded to the nearest hundredth. So to the nearest hundredth, what value are we approaching as h approaches 0? It's hard to see. Let me make it bigger. That's hard to see. Yeah, so I created this table. Okay, so there's my table. To 2 decimal places, what value am I approaching? Yeah, 403.43 if I round it. Agreed? Because look, as the ant walks from negative values, so on the graph as he walks from the left towards 0, getting closer and closer and closer, his y values are doing this. As he walks from the right, the other direction, towards 0, he gets some different values, but they're starting to agree, right? There's definitely a trend showing up here. To 2 decimal places, these both round to 403.43. So we know what the limit is to within 2 decimal places based on this table. Okay, so we got 2 strategies then for evaluating limits. We can look on a graph, or we can make a table and just choose values closer and closer and closer to that value, right? To see what the trend is. Now, there are problems with both of those, though, right? I mean, what if, we don't know, but what if this function actually did something really strange down here as we got closer to 0 that we just were missing? It's possible, unlikely, but possible. On the graph, well, this one worked great because those coordinates were integers. But what if that point had been out in here somewhere? Then it's harder, right? The graph isn't helping us as much. So we will come up with better ways to do this. Okay. So again, just summarize what I told you a second ago. There are 3 approaches to evaluating limits: numerically and graphically, which we're currently talking about, and better analytic approaches, where we're going to get an exact answer using algebra. Okay, and that's coming up. Okay, and I will, just like last year and the year before, all this stuff will be available on either Google Classroom or on Planbook, okay, by the end of the day. Um, okay, but are we good? Okay. So let's get even a little bit more precise here. We're going to develop an informal definition of a limit, and it's kind of intuitive. We can think of the limit of a function at a number a as being the one real number L that the functional values approach as the x values approach a. So the y value, functional value just means y value, right? Y equals f of x. Talk about a functional value, that's an output value. So the y value that the function approaches as x approaches, in this case we called it a instead of c, okay? Stated more carefully, it looks like this. Now let's wade through this. We're going to start to get into some more technical math jargon and language, and we got to be able to handle this. So we have to start off defining the pieces involved in this definition. Let f of x be a function defined at all values in an open interval containing a. What's that mean? If it's defined at all value, what's an open interval? We'll talk about it tomorrow, I guess, huh? Okay, I am going to build. Oh, yeah, I'll just get them tomorrow. Hang on to those. I forgot. Remind me at the start tomorrow, and I'll pick those up. I will. I'll put an assignment up that you can start on, but really, we'll finish up tomorrow.